Hey, hey, teach me how to do it. Hey, baby.
In the last lecture, we proved that if L over K is an extension of fields and f of x is a polynomial in K bracket x, then for any element sigma that is an automorphism of L fixing K, sigma has to permute the roots of f of x in L. One thing that this implies is that if you have sigma being in the automorphisms of L fixing K, then sigma permutes sets of K conjugate elements in L. So remember that two elements in L are K conjugate if they are roots of the same irreducible polynomial in K bracket x. Okay, so what we want to do at the start of this lecture is give some examples to see how to use these facts to better understand this group ought L over K. All right, so the first example, let's say K is Q, and L will be Q adjoined square root of 2 and square root of 3. So this is a field that we've studied before. We've seen, for example, that the degree of this extension is 4. So if you have an element sigma in ought L over K, and I'm going to continue to write L over K because I don't want to keep having to write Q adjoined square root of 2 square root of 3. So you have sigma in ought L over K. It has to send square root of 2 to plus square root of 2 or minus square root of 2. Why? Because sigma has to permute the roots of x squared minus 2. And there are these two roots, plus square root of 2 and minus square root of 2. So similarly, sigma has to send square root of 3 to plus square root of 3 or minus square root of 3. And once we've seen where sigma sends square root of 2 and square root of 3, we know where sigma sends any element of Q adjoined square root of 2 square root of 3. Why is that? I mean, what I'm claiming is that sigma is determined by where it sends these two elements, square root of 2 and square root of 3. That if I tell you sigma of square root of 2 and sigma square root of 3, then you know sigma applied to any element of this field. And the reason that that's true is this field is a 4-dimensional vector space over Q, and every element can be written as A plus B times the square root of 2 plus C times the square root of 3 plus D times the square root of 2 times the square root of 3, also known as the square root of 6, where A, B, C, and D are elements of Q. And if you have an automorphism of this field, then sigma applied to an element of this form is sigma of A plus sigma of B square root of 2 plus sigma of C square root of 3 plus sigma of D square root of 2 times square root of 3. And because, again, sigma is an automorphism, that is like sigma of B times square root of 2 is sigma of B times sigma of square root of 2. But sigma of A is A, sigma of B is B, sigma of C is C, and sigma of D is D, because sigma is an automorphism of this field fixing Q. So now we can see very concretely that if you know sigma of square root of 2 and sigma of square root of 3, okay, then that tells you sigma of square root of 2 times square root of 3, which is the product of sigma root 2 times sigma root 3. If you know those two special values of sigma, then you know what it does to any element. Okay, so there's two choices for sigma square root of 2 and two choices for sigma square root of 3. So there are 4 choices total that we could make. So there are at most 4 elements of this ought L over K. It's not clear that every one of these 4 choices actually gives an automorphism of this field. I mean, you can check very directly that, in fact, all 4 of these choices do give an automorphism. But the very last thing we'll do in this lecture is come back to this example and see that there really are exactly 4 elements of this automorphism group, that any one of these choices, for example, sigma could be an element that sends square root of 2 to negative square root of 2 and square root of 3 to square root of 3, that really does define an automorphism of this field. Okay, let's look at the next example. Let's say K is Q, and L is Q adjoin the fourth root of 2. So it's going to be useful to note that if you take the fourth root of 2 and you square it, you get the square root of 2. Well, so square root of 2 is in this field L. What does sigma, an element of aught L over K, do to square root of 2? Well, it permutes the roots of x squared minus 2. So it has to send square root of 2 to either plus square root of 2 or minus square root of 2, because it has to send this root of x squared minus 2 to another root of x squared minus 2. And what else do we know? Well, what does sigma do to this element, the fourth root of 2? Sigma permutes the roots of x to the fourth minus 2 that are in L. And there are only 2 roots of this degree 4 polynomial in L. There are 4 roots in a splitting field, but only 2 of them lie in this field. And that is fourth root of 2 and negative fourth root of 2. So sigma sends the fourth root of 2 to plus or minus the fourth root of 2. And whichever choice we make, this gives us information about what sigma does to the square root of 2, because sigma of the fourth root of 2 squared is sigma applied to the square of the fourth root of 2, which is sigma square root of 2. And whichever choice we make for sigma fourth root of 2, either plus fourth root of 2 or negative fourth root of 2, when we square it, we get the positive square root of 2. So we're seeing that sigma square root of 2 must be square root of 2. So what are we seeing here is we have this information that sigma has to send a root of x squared minus 2 to a root of x squared minus 2. So sigma root 2 has to be positive square root of 2 or negative square root of 2. But then we have more information about how sigma acts on elements of this field L, and we can use that information to see that, in fact, sigma of square root of 2 equals negative square root of 2 is not possible. So this is an example where no element sigma in the group of automorphisms of L fixing K sends square root of 2 to negative square root of 2, even though they have the same minimal polynomial over Q. So we have to be careful in thinking about a converse to the kind of statement up here. We know that sigma has to send a root of x squared minus 2 to another root of x squared minus 2, but we can't always just pick another root and say, okay, there is a sigma that sends my first root to my second root. Okay, so I'm going to pause and erase, and we'll talk about another example. Let's talk about 2 more examples. Let's say that K is Q and L is the field generated over Q by the cube root of 2 and zeta 3, a primitive cube root of unity. The polynomial x squared, I've written this incorrectly, x cubed minus 2 has 3 roots in L. It has the cube root of 2, the positive real number that cubes to 2, cube root of 2 times this primitive third root of unity, and the cube root of 2 times the square of our chosen positive third root of unity. You can think of this as being e to the 2 pi I over 3, if you would like. So what do we know? We know that any sigma in aught L over K has to permute these 3 roots, right? So the sigma has to permute the roots of this polynomial that are in L. So we get some permutation. And a question you could ask is, okay, we're permuting 3 elements. There are 6 possible permutations. Are all 6 possible permutations realized by some element sigma in aught L over K? So what I mean is, suppose you want to find a permutation. Is there a sigma, for example, that sends this first root to the third root, the second root to itself, and the third root to the first root? Okay, so this is the kind of question that we would like to understand about roots of polynomials and these groups, automorphisms of L fixing K. All right, another example. Let's say K is Q, and now L, instead of just being Q adjoin the fourth root of 2, let's say L is the field generated over Q by the fourth root of 2 and I. So now L this polynomial x to the fourth minus 2 has 4 roots in L. It has plus or minus the fourth root of 2 and plus or minus the fourth root of 2 times I. So any sigma in aught L over K has to permute these 4 roots. And you might want to know, are all 24 4 factorial possible permutations realized by elements sigma in aught L over K? If I give you some permutation of these 4 elements, does there exist some element sigma in this group of automorphisms such that the way that sigma acts on this set of 4 elements in L is by that chosen permutation? Okay, so these are the kinds of questions we would like to understand better. And what I'll say for now is it's not always true, but for certain special extensions L over K, any 2 K conjugates, alpha and beta, in L are related by aught L over K, by which I mean there exists a sigma in the automorphism group of L over K, so an automorphism of L fixing K, such that sigma sends alpha to beta. So if alpha and beta are roots of the same irreducible polynomial in K bracket X, there exists an automorphism of L fixing K that sends alpha to beta. Okay, so we want to understand what kinds of permutations we get applied to these special finite sets, roots of a given polynomial, as we vary over all elements in this group aught L over K. And okay, if we want to understand that kind of question, we should understand some more about this group aught L over K. In particular, how big is it? So I'm going to pause and erase, and I'll prove an initial result in that direction that we'll improve on later in the lecture. We would like to better understand the set or the group of automorphisms of L fixing K. So the first thing that we're going to prove in this direction is just about the size of this group. Theorem 3.1 in Conrad's Galois correspondence notes says, let's say that L over K is a finite extension of fields. Then the group aught L over K is finite. And here's the proof. Well, we know a lot about finite extensions. In particular, we know that a finite extension of K is generated by finitely many algebraic elements over K. This is something we proved several lectures ago. So let's choose such a set of finitely many algebraic elements over K that generate L. So L is the field generated over K by alpha 1 up through alpha n. All right, now sigma, an element of aught L over K, is determined by where it sends alpha 1, where it sends alpha 2, where it sends alpha 3, up to where it sends alpha n. Why? Because we have this description of the elements of K adjoin alpha 1 up through alpha n as polynomials with coefficients in K in these variables alpha 1 up through alpha n, where the tricky thing is understanding the degree in each one of these different variables. But just because sigma is an automorphism of this field, it is clear that if I tell you the values of sigma of alpha 1, sigma of alpha 2, up to sigma of alpha n, then I'm telling you the value of sigma of alpha 1 to the d1 times alpha 2 to the d2 times alpha 3 to the d3, and so on. Okay, so how many choices are there for this set of n values and elements in L? Well, sigma permutes the roots of the minimal polynomial of alpha I over K, the roots of that polynomial that lie in L, right? So what is this? What am I saying here is that sigma permutes the set of K conjugates of alpha I in L. So where does sigma send alpha 1? It has to send it to another root of the minimal polynomial of alpha 1 over K that lies in L. So how many choices are there? It depends on the degree of this minimal polynomial. And really, it depends not just on the degree, but how many roots of this polynomial lie in L, but it's at most the degree of this polynomial. So the important thing is that there's only finitely many choices for where you send each one of these alphas. So if there's finitely many choices for where to send alpha 1, finitely many for where to send alpha 2, and so on, finitely many for where to send alpha n, then the total number of these automorphisms of L, fix, and K is at most the product of the number of the product of this first number of choices times the second number of choices times the nth number of choices. So the product of finite things is finite, and that completes the proof. Okay, so this shows that this group is finite, but it tells you very little about how to actually compute what this group is in particular examples. Sure, I mean, if you knew the minimal polynomials of each of these n elements, that would give you some kind of a bound. But what we're going to do is think about this in a different way and prove a better bound in a particular case. So not just that this group is finite, but we're actually going to say how big this group is. So the question is, can we prove a better bound than this? And the answer is yes, specifically, at least in the case where L is a splitting field over K, meaning there exists a polynomial f of x in K bracket x such that L is a splitting field for f of x over K. And I guess what I should say is in the case where there exists a separable polynomial f of x in K bracket x such that L is a splitting field for f of x over K, there we'll be able to say something even better.